So next topic is equivalent circuits with respect to the passive elements RLC. So before writing these equivalent circuits with respect to RLC, we need to understand first one, when two elements are connected in series. When two elements are connected in series, then the current is same. Current flowing through the series elements is same. That is the first point to be noted. So whenever two elements are connected in series, then the current flowing through the two elements is same. And the second one is when two elements are connected in parallel. When two elements are connected in parallel, voltage is same across the two elements which are connected in parallel. So what is the meaning means, when two elements are connected in series, current flowing through the elements is same, but the voltage will be different based on their values. Current is same, but the voltage will be different. Voltage will be divided. And here, when the elements are connected in parallel, current is divided and the voltage is same. Current will be divided based on their values, but the voltage is same. So here, in a series elements, voltage will be divided, but current is same. And in parallel connection, current will be divided, but the voltage across the elements is same. Voltage will be divided. So from this, voltage division rule can be written, and from this, current division rule can be written. So we'll see step by step. And the third one is maximum resistance offer minimum current, and vice versa. If the value of resistor is more, then the current flowing through the element is less. If the resistance value is less, then the current value will be more. And if the value of resistor is 0, then the current is nothing but the total current flowing through the circuit. Total current. That means current always tries to flow through a minimum resistance path. So that is an important point to be remembered. So we'll see first of all for a series circuit. So in the series circuit, what we can derive means we can derive voltage division principle, because in the series circuit, current flowing through the elements is same, but the voltage is not same. So current is same, but voltage is not same across the elements or between the elements. So here I am taking a circuit such that two elements are connected in series in a particular circuit. So this is the element having impedance Z1 and element having impedance Z2, and this is the voltage applied. So net current flowing is I. So therefore the current flowing through the elements is same, but the voltage will be different based on the parameter value here. So Z1 is offering some impedance and Z2 is offering some impedance. So therefore these two will be different. So from the Ohm's law, V is equal to I into Z equivalent value. So but from the KVL, if I apply KVL, it should be V is equal to V1 plus V2. The summation, algebraic sum of the voltage drops is equal to applied voltage. So therefore I can write V is equal to, from this equation, so I am writing here I1 into Z1 plus I1 into Z2, because I2 and I1 both are same in series, current flowing through is same. So I am writing here V is equal to, I am putting I into Z1 plus Z2. So therefore if you compare these two equations, Z equivalent is equal to Z1 plus Z2. So in a series elements, the total equivalent value of impedance is equal to algebraic sum of all the values. If I take for a resistor, R equivalent is equal to R1 plus R2 plus R3, so on. How many elements are connected? So that much elements will be added. So for a inductor, it will be L1 plus L2 plus L3, so on. Similarly, for a capacitor, it can be written as 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus so on. So for the capacitor, it will be like this. So this is related to a series circuit calculation, and here voltage is dividing voltage, this entire source voltage is divided into V1 plus V2. So this can be written as, this V1 can be written as per the voltage division rule, total applied voltage V into this impedance Z1 divided by total impedance Z1 plus Z2. Similarly, voltage across second element V2 can be written as total voltage V into this impedance Z2 divided by total impedance Z1 plus Z2. So these are the voltage division rule formulas for particular elements. So voltage division rule of a particular element can be written as total applied voltage into that impedance divided by total impedance. So in a generalized way, Vn is equal to total applied voltage V into Zn divided by Z1 plus Z2 plus Z total impedance, Z equivalent value, or we can replace with a Z equivalent value. So this is regarding series connection. Next one is parallel circuit. Parallel circuits. If I am considering a parallel circuit here, Z1, Z2 applied across a voltage source plus minus V, total current I, current will be divided but the voltage is same across the elements. So V is nothing but I into Z equivalent value. So from this I can be written as V by Z equivalent values. So here by KCL applied at particular node X, the total current I is equal to I1 plus I2. So it can be written as I1 is nothing but total voltage V by Z1 plus V by Z2. So I can be written as V by Z from this formula. So V by Z equivalent value is equal to V by Z1 plus V by Z2. So take V and common, then Z equivalent value will be here. 1 by Z equivalent is equal to 1 by Z1 plus 1 by Z2. So this is for two elements. If I take resistor, 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus so on. If I write for inductor, 1 by L equivalent is equal to 1 by L1 plus 1 by L2 plus so on. Whereas for capacitor it is C equivalent is equal to C1 plus C2 plus so on. So these are the formulas for calculating or finding the total equivalent values when the elements are connected in parallel. And from this current division rule, so here current is divided, so current division rule can be defined as current division rule current and any branch, current in any branch can be written as total current flowing through the circuit into opposite branch resistor, opposite branch impedance value. It may be resistor or a inductor or a capacitor. Opposite branch impedance divided by sum of the impedances.